When amateur astronomers look up at the night sky and track the motion of the moon, planets, or even long period comets, we're seeing Newton's universe in action. Few individuals have shaped astronomy more profoundly than Sir Isaac Newton, whose work finally explained why the heavens move the way they do. Newton was born in 1643 in Woolsthorpe, England, arriving prematurely and into a difficult family situation. His father died 3 months before he was born, and as a result, he was fatherless, and his mother remarried quickly and married a minister. The minister moved his mother away from Isaac and kept Isaac away from the children they had together. 9 years later, the minister died, and Newton was reunited. So Newton grew up intensely curious, often solitary. This inward focus turned out to be really a gift to science. It was also the separation that people speculate caused Newton to have anxiety and also to be lacking some of the social skills necessarily he had. And we can see that later in life as he so vehemently defended people who opposed him. After going to grammar school, he went to Trinity College in Cambridge. He immersed himself in the works of Galileo, Kepler, and Descartes, thinkers who were beginning to describe the universe mathematically. But it was during the plague years of 1665 to 66, when Cambridge was temporarily closed, Newton returned home. The real breakthroughs began coming. Before Newton, astronomers could describe how planets moved using Kepler's law, but no one truly understood why they moved that way. They just kind of accepted that Kepler was correct, but Newton's answer changed everything. He proposed the law of universal gravitation, showing that the same force causing an apple to fall to the ground, didn't hit him in the head, also governs the motion of the moon and the planets. Suddenly, with Newton's discovery and explanations, the Earth and the heavens were no longer separate realms. They were part of a single physical system ruled by the same laws. He explained the why behind it. Newton's 3 laws of motion, published in Principia 1687, gave astronomers the mathematical tools to predict planetary orbits, comet paths, tidal forces, orbital perturbations between planets. Basically, every spacecraft trajectory calculated today still relies on these same basic principles. They may be expanded upon, but they come back to the 3 principles, his first 3 laws, which you can see here. Body in motion remains in motion. A body at rest remains at rest. Force equals mass times acceleration. For every action, there is an equal and opposite reaction. He didn't stop there. He didn't work with just theory. He built the first practical reflecting telescope, replacing lenses with mirrors and eliminating that color distortion we call chromatic aberration. Nearly every large telescope design used by modern observers and observatories today traces directly back to the Newtonian concept, including the basic Newtonian reflector that many amateurs use today, including myself. It helped Herschel to be able to develop his telescopes and allowed him to be able to see deeper and farther than anyone before him. And we'll talk about Herschel as we get going later on. To make all this work mathematically, Newton developed calculus. So if you've ever had to take calculus, which I have, you can thank Newton for all the frustration you felt. But it gave science a language capable of describing motion, acceleration, and gravitational interaction. With calculus and mechanics together, astronomy transformed from descriptive observation into predictive sciences. It was Newton developed it in 1666. Wilhelm Leibniz began publishing it in 1668, and that led to a really big conflict between them, as Newton really personally attacked him and said, "Nope, I had it first." Later life and recognition, Newton later became president of the Royal Society, oversaw reforms of English coinage at the Royal Mint, became the master of the Royal Mint, and actually persecuted counterfeiters, even leading to some being put to death by hanging. He was knighted in 1705, and in later life he continued to expound upon his writings and put them together. When he died in 1727, he was buried with distinct honor in Westminster Abbey. His tomb you can still see in Westminster Abbey, as is shown here. This is a rare honor for a scientist. Usually you were nobility or royalty to be buried in Westminster Abbey. It reflected how deeply his discoveries had reshaped the world. Why does he still matter to us today? Every time we compute an orbit, predict a planetary conjunction, or track the return of a comet, we're applying Newton's understanding of gravity and motion. Modern astrophysics has expanded far beyond Newton, but the framework he built still underpins nearly all practical astronomy, from backyard observing to interplanetary navigation. When we set up a telescope under dark skies, it may not feel like we're using 17th century science, but nearly everything we observe depends on Isaac Newton's work. Planetary motion, the steady march of Jupiter across the background stars through Gemini right now, the predictable positions of Saturn's rings each year, and even the timing of planetary oppositions all rely on Newton's laws of motion and universal gravitation. The same equations he developed allow astronomers to calculate where every planet will appear decades or centuries ahead of the time. When a periodic comet returns exactly on schedule, we are watching Newtonian gravity in action. Once astronomers understand that comets orbit the sun like planets, their paths could be calculated precisely, turns mysterious visitors into predictable celestial travelers. Binary star systems, where two stars orbit each other over decades or centuries, follow the same gravitational laws Newton described. Measuring those motions allows astronomers to determine stellar masses, one of the most powerful tools in astrophysics. Many amateurs, including myself, observe with Newtonian reflector telescopes, a direct descendant of the instrument Newton built in 1668. By replacing lenses with mirrors, he eliminated chromatic aberration and created the optical design that still dominates large observatories today. Even modern spacecraft navigation, planetary flybys, lunar missions, and asteroid encounters still begins with Newton's gravitational equations. More advanced corrections are applied, but in the very real sense, every deep sky mission starts with Newton. So when you're at the eyepiece, every tracked orbit, every predicted eclipse, every telescope using mirrors reflects Newton's legacy. When we observe the moon's motions night to night or follow a planet through the constellations, we're watching the universe behave exactly